In this presentation, I stress the anti-synergy between adsorption and diffusion in faujasite zeolite. In practice, zeolites are used in their cation-exchanged form, and depending on the silicon to aluminum ratio, they are either called X zeolites or Y zeolites. X zeolites have silicon to aluminum ratio 1 to 1.5, and Y type zeolites have silicon to aluminum ratios between 1.5 to 3. The variety of extra framework cations that are used, for example, lithium, sodium cations, or barium. Barium X zeolites are used for xylene separations. Lithium X zeolites are used for nitrogen-oxygen separations and for flue gas applications in which CO2 requires to be captured. The extra framework cations are commonly the sodium cations. Let's have a look at the structural topology of our zeolites. These consist of cages of approximately 11.5 angstrom. Each cage is separated from adjacent cages by 12-ring windows that have apertures which are approximately 7.2 angstrom. Let us examine the key properties such as polarizability, dipole moment, and quadrupole moments of gas molecules such as carbon dioxide, methane, carbon monoxide, nitrogen, and oxygen. Here I plot the polarizability versus the quadrupole moment. And we note that the polarizability of methane is practically the same as that for carbon dioxide, but carbon dioxide has a significantly higher quadrupole moment. We also note that the quadrupole moment of nitrogen is about a factor 4 higher than that of oxygen. Of these gas molecules, only carbon monoxide has a dipole moment. For separating CO2 from methane, we can exploit the large difference in the quadrupole moments between CO2 and methane. Methane has a 0 quadrupole moment by electrostatic interactions with the extra framework cations. Similarly, the selective adsorption of nitrogen from mixtures with oxygen is achieved because of the large quadrupole moment of nitrogen that is 4 times larger than that of oxygen. For CO2 capture from flue gases, we rely on the large differences between the quadrupole moments of CO2 and nitrogen. And also the polarizability of CO2 is higher than that of nitrogen. Let us examine the electrostatic interactions between a gas molecule and the extra framework cation. That can be either lithium, sodium, potassium, magnesium, calcium, strontium, or barium. I also indicate here the size of the cation, the radius of the cation in angstrom values. That R represents the distance between the center of the gas molecule and the center of the cation. Basically, we can distinguish between three types of electrostatic interaction potentials. One due to induced dipoles. The second one due to the interaction of the electrical field with the permanent dipole of the guest molecule. And thirdly, we have the interaction of the electrical field gradient with the quadrupole moment of the gas molecule. Here Q represents the charges of the extra framework cation, and R is the distance from center to center between the guest and the cations. In all cases, we note that the potential energy of interaction is proportional to the charge, or the square of the charge, and inversely proportional to the distance to the power 2, distance to the power 3, and the center to center distance to the power 4. In other words, larger electrostatic interactions are achieved with smaller cations because the center to center distance is smaller if the radius of the extra framework cations is smaller. The electrostatic interactions increase with the valency of the extra framework cation. A bivalent barium cation would contribute to a greater extent to the electrostatic interactions. And larger dipole, larger quadrupole, higher polarizability will all lead to larger magnitudes of electrostatic potentials. In this slide, I would like to demonstrate the anti-synergy between the adsorption strengths and the mobility of a gas molecule. And as an example, let's take carbon dioxide. The binding strength or the binding energy is reflected in the isosteric heat of adsorption, and the mobility can be quantified by the self-diffusivity of CO2. Both these parameters, the isosteric heat of adsorption and the self-diffusivities, are plotted as a function of the surface potential that serves as a proxy for the spreading pressure. The reason for the choice of the surface potential as x-axis is clearly explained in my presentation on the spreading pressure that is available on my YouTube channel. With increasing number of extra framework cations, as we move from all silica faujasite to NaY zeolite with a silicon to aluminum ratio of 2.55 to NaX zeolite with a silicon to aluminum ratio of 1.23, we note that there is a significant increase in the isosteric heat of adsorption. In other words, the strength of binding increases with the number of extra framework cations, in this case sodium. This is to be expected because of the large quadrupole moment of CO2. However, stronger binding implies lower mobility, and we note from the plot of the self-diffusivity versus the surface potential that the mobilities decrease with increasing number of extra framework cations. As we move from all silica faujasite to sodium Y to sodium X. So the takeaway message from this slide is that the stickier the molecule, the lower is its mobility. The takeaway from the previous slide is that we should not go overboard in trying to increase the binding strength by adjusting the silicon to aluminum ratio in faujasite zeolites. Strong binding leads to lower mobility, and therefore diffusional influences are enhanced. For operations in fixed bed adsorbers, strong diffusional influences lead to distended transient breakthroughs, and this causes a reduction in the productivity of the desired product. Further details are available in my YouTube presentation on transient breakthrough simulations that discusses in detail how diffusional influences affect performances of fixed bed adsorbers. A further point to note is strong adsorption also requires a deeper vacuum for desorption, and therefore in choosing the silicon to aluminum ratio to be used in faujasite zeolites as adsorbents and fixed bed adsorbers, we need to take into account the entire adsorption-desorption cycle along with diffusional influences before making the appropriate choice of the degree of to which extra framework cations need to be added. Cation-exchanged faujasite zeolites also find use in membrane constructs in which a thin layer, typically 50 micrometers of the zeolite, is used as a perm selective device to separate gaseous mixtures. The permeation selectivity is a product of the diffusion selectivity and the adsorption selectivity. Let's look at the relative values of the adsorption selectivity and diffusion selectivity for all silica faujasite, for sodium Y and sodium X. With increasing amounts of extra framework sodium cations, the adsorption selectivity of CO2 with respect to methane increases by about 2 orders of magnitude in going from all silica to NaX that contains 86 aluminum atoms per unit cell. However, the increase in the adsorption selectivity is at the expense of diffusion selectivity, and NaX zeolite has a diffusion selectivity of CO2 with respect to methane that is about 1 order of magnitude lower than that of all silica faujasite. The decrease in the diffusion selectivity is due to the fact that CO2 is much more strongly adsorbed, is much less mobile than methane. The net result for use in membrane constructs is that while adsorption selectivity increases with increasing number of extra framework cations, the diffusion selectivity decreases, and the permeation properties of the membrane is a reflection of the anti-synergy between adsorption and diffusion. Let us see how that plays out. Consider the permeation of 50-50 feed mixtures of CO2 and methane at a temperature of 300 degree Kelvin and a total fugacity of 1 megapascals. This is a Robson plot of the CO2 methane permeation selectivity plotted against the CO2 permeability. The best performance of any membrane is in the top right-hand corner. We would like a performance that is right at the top right-hand side of the Robson plot. This line represents the Robson upper bound, and I present here the data for NaX, NaY, and all silica faujasite. These data are calculated on the basis of a combination of molecular simulations of mixture adsorption and MD simulations for mixture diffusion. We note that by increasing the number of extra framework cations, the permeation selectivity increases, and therefore increasing the number of cations is a beneficial thing from a permeation selectivity viewpoint. However, we note that the permeability, which is related to the mobility within the membrane, is reduced by about 1.5 orders of magnitude in going from faujasite to NaY to NaX. And therefore, there is a trade-off between permeability and permeation selectivity in choosing the right silicon-aluminum ratio to be used in membrane constructs.